morning, ladies and gentlemen. Today I'm going to talk about the carbon nanotube reinforced mortar that we use as a sensor to monitor the structural health of restored marble epistals that we subjected to shear loading. This work was conducted at the National Technical University of Athens in collaboration with the Technological Educational Institute of Athens. Cultural heritage monuments of the classic area are constructed using marbles that are connected together using iron elements, which are placed in specifically calcium grooves, which were then filled with molten lead. Over the centuries, due to corrosion and also mechanical loading, a lot of those connections had fractured, and there is a project at the Athens Acropolis and at the Parthenon for restoring these fractured connections. It's on the way for a long time now, and the iron is substituted by titanium due to its improved corrosion resistance, and lead is substituted by a cementitious mortar. But however, we have seen that a fracture has also occurred at the restored marble epistals. Typical approaches in order to monitor the structural health of these restored monuments involve the use of strain gauges, LVDTs, and extensometers. All of them provide information on the specific locations of the outer surface of the structure. Failure mechanisms, however, that led to the fracture of these restored marbles initiate from inside the structure. However, traditional monitoring techniques cannot detect any damage that occurs inside the material. Our idea is to use the innovative carbon nanotubes in order to reinforce the filling material, the mortar, and to use this nano-reinforced mortar in order to monitor the structural integrity of the restored monuments. And we decided to use carbon nanotubes due to their exceptional piezoresistive characteristics. This means that their electrical properties are changing according to the applied stress and strain. So what we wanted to do is to develop a smart material that can be used as a sensor by recording its electrical resistance change, which is a non-destructive testing method. In order to do that, we produced several specimens which were composed of two marble blocks. A groove was sculptured inside these blocks. The marble was a Dionysus marble. It's a typical marble that's currently used at the restoration project. For filling the groove, we prepared a cement mortar with white cement and coarse quartz sand, a fine sand and a coarse sand, and the carbon nanotubes were dispersed inside the mixing water with the aid of a new generation polycarboxylate-based ether superplasticizer, which is typically used in cementitious materials, and with the application of ultrasonic energy. And what I want to point out is that these materials, the matrix, the raw materials, and the mixing, it was based on the material that's currently being used at the restoration of the Parthenon. So we mixed the materials using the standard. We filled the groove with a nano-reinforced mortar, and then we placed inside the eye-shaped titanium connector. Please note that on the surface of the connector we placed three strain gauges, one at the fixed marble, one at the interface of the two marble blocks, and one at the movable marble. This is the placement of the connector. We filled up the groove with a nano-reinforced mortar, and immediately after casting we placed 4 electrodes inside the mortar in order to use them for the measurement of the electrical resistance. And we cured the specimens for 28 days. During loading, marble block 1 was fixed, while an upwards displacement was induced at marble block 2 using a specially designed loading and restraining system. The experiment was performed using displacement control. Then electrical resistance of the nano-reinforced mortar was monitored using the first 4 electrodes. The 2 electrodes in the middle were used to measure the voltage, and the 2 electrodes at the outer electrodes were used to apply the direct current. We also used acoustic emission technique. 8 different acoustic emission sensors were placed at strategic locations around the specimens. And we also performed digital image correlation in order to capture the displacement field at the front of the specimen using 2 different cameras. And at the rear of the specimen, 2 clip gauges were placed to monitor the relative displacement of the 2 marble blocks, and also here you can also see 2 more acoustic emission sensors. And I would like to show you some pictures of the experimental setup. So moving at the results, this slide, the load time curve is being shown. If we exclude the initial part, if we look at this part between point A and point B, the curve is pretty linear, and it reaches point B at a load of around 25.5 kilonewtons. After point B, the curve ceases to be linear, and it reaches a maximum, at a local maximum at point C, which is at 27.5 kilonewtons. This deviation from a linearity can be explained due to the yielding of the connector. And if we look at the results of the strain gauges, which, if you remember, were attached on the connector, the orange line are the results of the strain gauge placed at the interface between the 2 marble blocks, while the blue line are the results of the strain gauge placed on the movable marble. So it's observed that a load approximately higher than 27 kilonewtons, there is a big deformation occurring on the connector. Between C and D points, there is a small decrease of the load, approximately 1 kilonewton, and then the load starts increasing again linearly up to point E, where there is a slope change, and ultimately a failure occurs at point F at a load of 31.5 kilonewtons. Looking at the results of the electrical resistance change in comparison with the applied load, the electrical resistance change is the red line, while the applied load is the blue line. It is observed that the electrical resistance is changing analogous to the applied load up to point 1. This is a very encouraging result, which shows that this technique can be used for monitoring the stress strain of the restored marble epistyles. After point 1, there is this peculiar response of the electrical resistance oscillating up and down up to point 2. According to previous studies, this point 1, which is at around 1,700 seconds, it's the onset of microcracking. So due to the local fractures that occur inside the mortar, there is some disruption of the electrical paths, and that's why we observe this response. After point 2, there is a decrease and then a small increase of the electrical resistance. In order to explain that, we can look at the results of the clip gauges which were attached at the rear side of the specimen. The orange line is the block's relative opening displacement curve. If we exclude the first part, the similarity of this curve with the load time curve is astonishing. And what I would like you to notice is that at the load of 27.5 kilonewtons, and there is also a decrease in the displacement. What this means is that the 2 blocks are coming closer together. So the nano-reinforced mortar is coming closer together, and this can explain this decrease. So when the material is coming closer together, the electrical resistance is decreasing, while when we have tensile stresses, the electrical resistance is increasing. And moving at the results of the digital image correlation and the acoustic emission, on the left, in order to take advantage of the data of the DIC, what we did is we isolated two small rectangle areas at the front of the specimen, exactly next to the block's interface. And here you can see the displacement of the center of those two rectangles along the x-axis. So it is observed that up to a time of 1600 seconds, the displacement of both blocks is increasing. Here, there is a change in the response. The displacement of the movable part starts increasing a little bit more. This is the onset of microcracking, and also at the 1700, which is very close to the point where the oscillation of the ERC, the electrical resistance change graph was observed, we can see that there is a split of the mortar, and the fixed part moves on the other position. And looking at the results of the acoustic emission, again, it's evidence that the first, I would like to mention that these are the cumulative number of acoustic events that happens at the center of the specimen, again. So the first event happens at point A of the load time curve, and the events are starting increasing, and they exponentially increase around point B, where is the where the connector starts yielding. Some images very fast. These are images after fracture. The fracture occurred at the interface between the nano-reinforced mortar and the titanium. The experiment ended when the marble has fractured, and it's clear that the connector has deformed. I'm not going to stay to recap, just two very important points, that it seems that the use of multiple carbon nanotubes to reinforce the mortar can actually develop a material that can be used to act as a sensor, strain sensor and pre-failure indicator. And also it's we're very happy because the data of the electrical resistance change are in a very good agreement with traditional techniques, with the results of the clip gauges, the strain gauges, and also with the results of the DIC and the acoustic emission. Thank you very much.